Hello everybody. So the last time we developed a formula to use a summation that gave us an approximation for an area under a curve, we were using rectangles. And with those rectangles, we were dealing with either left hand, right hand, or possibly midpoint sections, or possibly sections that had unequal width. But we developed that to give us the Riemann sum integral. However, sometimes it's not as easy to find the value of the definite integral without an approximation technique. So this discussion will go over two of them, the first of which is what we call the trapezoidal rule. As we know, the area of a trapezoid is equal to 1/2 its height times the sum of the bases, base 1 and base 2. So if we think about this for our area under a curve, it would be just as easy for us to select values on our curve starting at x of 0. Get my thing to cooperate with me. Starting at x of 0, and then working our way across x1, x2, and so on down the list until we get to the ith rectangle, xi sub 1 and x sub I define the left and right hand sides, and these values right here are going to give us our width. So we think about our delta x being b minus a over n, that is our delta x, and if we take 1/2 delta x as the height, and then the sum of f of x sub 1 minus x of x I minus 1 and f of x of I, we're going to get the area of that rectangle. And so our summation would involve 1/2 times delta x, which we consider to be b minus a over n, times the sum of all of those I rectangles. Well, if we were to expand out those rectangles and reduce the formula we get, here it is, it would be f of x of 0 plus 2 f of x of 1 plus 2 f of x of 2. And you can see that if we expand this out and say that we're actually adding the first rectangle's height plus this second rectangle's height for the first rectangle, but then this first rectangle's height plus this second rectangle's height for the next one. So we're counting this first height twice, this next height twice, this third height twice, and so on down the line until we get to b, which is our x of nth height, which we don't count twice. So if we were to take this limit of this summation as n went to infinity, we would in fact get the area from a to b of f of x dx. And that's what we're after here. Now the best way to illustrate this is by example. So let's consider an example where we want to approximate the interval 0 to 2 of 1 over x cubed dx using the trapezoidal rule with n equals 4. Now, I will point out that the integral of the antiderivative of 1 over 1 square root of 1 plus x cubed dx is not an easy integral that we can handle using elementary methods. And when I say elementary methods, we mean something like we could use a substitution method. We might be able to find a trigonometric function that fits or something else, but there's no elementary function that seems to fit it. So an approximation is a good tool to use. All right, so how does this proceed? We proceed just like we would have proceeded if we were going to do a summation of rectangles underneath the curve, only this time there's going to be the slight change using our formula right here. So let's see. Delta x is the same as the delta x we've ever dealt with. That is, each delta x is calculated by taking b minus a divided by n, the number of rectangles or shapes we're using. In this case, trapezoids. And each width of each rectangle, or trapezoid in this case, it's a trap, is 2 minus 0 over 4, that is to say 1/2. So if we were to start with our rectangles over here, or trapezoids, I keep getting them mixed up, we're going to start at 0. Of course, that is the first x value that we use right here, but then we keep on going. The first rectangle is 1/2 away from that, so that's our new x of 1. The next rectangle would be 1, then we'd be at 3/2, and then we'd be at 2 right here, right? So we're going from 0 to 2 on that interval. Each rectangle, each trapezoid will have a height h equal to delta x. So we're going to take 1/2 delta x, I should say delta x in here, 1/2 delta x times f of x of 0 plus 2f of x of 1 plus 2f of x of 2 and so on down the line to f of x of 4. That means that we're actually substituting in here. So we're taking 1 over the square root, in this first case, of 1 plus 0 cubed. We know that's going to come out to be 1. And I've done this with each of the other ones right here. Let's say we substitute in 1/2. We'll have 1 over the square root of 1 plus 1/2 cubed. When I work that out, that actually comes to be 2 times the square root of 2 over 3. And I've done this subsequently with each of the different values, and I get the square root of 2 over 2 right here for this next one. I get 2 square root of 2 divided by the square root of 35 here. Kind of interesting that I do. And I get 1/3 here. Wait a minute, not 1/3. 1 plus 2 cubed. Oh, that's 1/3, right? Square root of 9, right? There it is. Okay. We multiply each of these values by this multiplier right here that we see in this trapezoidal method. So it's f of x of 0. So we just take 1 as our first value. We take 2 times each of our subsequent values right here. So we're going to take 2 times 2 square root of 2 over 3. That's 4 square root of 2 over 3. I take square root of 2. 2 times square root of 2 over 2 is just square root of 2 right there. I take 4. And this time I rationalize my denominator. So I get 4 square root of 70 over 35. And then my last one, I get 1/3 right here. Our area is going to be 1/2 times delta x times the sum of all of these. So our area, our definite integral, would be approximately equal to 1/4, 1/2 of delta x times this summation, 1 plus 4 root 2 over 3 plus square root of 2 plus 4 square root of 70 over 35. Lovely numbers. Plus 1/3. All right. Of course, doing a little bit of a fancy footwork here mathematically, you could work this one out. And I found an expression that looked kind of like this: 1/4 of the quantity 140 plus 245 square roots of 2 plus 12 square roots of 70, all divided by a common denominator of 105. Sort of an unwieldy fraction to work with, but I approximated that for my decimal to 5 decimal places right here. I found 1.39734, which is pretty good for a approximation right here. You might actually try and work this through yourself just to see, but this is the way that we work the trapezoidal method. Not terribly difficult, but you do want to pay attention to 1 or 2 small items. Again, those multipliers are the important part of this, along with each x of n times each value of the function at that point. Doing so should give you about the right approximation value we need.